All right, let's dive straight into this explainer. Today, we're going to see how we can take abstract, kind of intimidating math formulas and transform them into a really practical toolkit for predicting the real world. Welcome to what I like to call the complexity ladder of probability distributions. We're going on a bit of a journey, starting from the absolutely simplest mathematical event possible, and we're going to climb that ladder rung by rung until we're literally modeling the chaos of manufacturing, medicine, and even human behavior. Let's get to it. But before we take that first step up the ladder, we have to talk about the granddaddy of all probability divides. It's the split between counting distinct things and measuring continuous things. Think of discrete probability as, well, anything you can physically count on your fingers, like rolling a dice or flipping a coin, right? They're distinct, totally separate events. But continuous probability? That's about measuring our infinitely divisible reality. Imagine trying to find the exact microscopic weight of a single raindrop, or the precise length of a piece of string down to the atom. This one core divide dictates every single tool we're going to look at today.
So here is our roadmap for the explainer today. First, we'll cover the two types of probability, then we'll look at Bernoulli and binomial models, move on to Poisson, where timing is everything, then hit the continuous normal distribution, and finally wrap up by standardizing the normal curve.
Okay, part one, the two types of probability. Let's start right at the bottom of our ladder with discrete versus continuous. Take a look at this. This is the absolute atomic unit of probability. We're talking about a single experiment or process that gives you only two possible outcomes. This is the Bernoulli distribution. Think of it like a light switch. It's either on or it's off. It's a success, which we mathematically just label as a 1, or a failure, which is a 0. That little parameter P you see, that simply represents the probability of that success happening. It doesn't get simpler than this. It's the most basic discrete distribution out there, but it is the absolutely essential building block for everything we're about to do.
Which brings us to part two, Bernoulli and binomial models. Let's see what happens when we start stacking up those single events.
Now, what's really fun is how we can apply this math to highly relatable, maybe slightly stressful situations. Like trying to figure out the exact chances of a student, let's call him Sipun, getting 3 answers right on a test, purely by guessing. Let's say Sipun missed class, did absolutely 0 revision, we've all been there, right? And now he's staring down a 5-question multiple-choice paper. If every question has 4 choices and only 1 is correct, we can actually mathematically predict his fate. Because we're now looking at multiple discrete events, those 5 specific questions, we've actually stepped up from the simple Bernoulli switch to what's called the binomial model. But to solve Sipun's dilemma, we can't just plug numbers in wildly. The binomial distribution only works if 4 very strict conditions are met. First off, every question has to have only 2 outcomes. He gets it right or he gets it wrong. Second, there has to be a fixed number of trials, which we call n. For our guy Sipun, n is exactly 5 questions. Third, the trials must be independent. Guessing question 1 can't magically help him guess question 2. And finally, the probability of success, p, has to be exactly the same every single time. Since there are 4 choices per question, his chance of a correct guess is locked at 25%, or 0.25. Because all 4 of these rules perfectly apply here, we can run the binomial formula and find out his exact chances of getting a 0 or, fingers crossed, 3 right. But it's not just for bailing out students on multiple-choice tests. Professional statisticians use this exact same model for absolutely vital real-world tracking. Take a look at this scenario, calculating the expected number of survivors out of 40 patients undergoing therapy for kidney cancer. In this case, our fixed number of trials, our n, is those 40 patients. The probability of survival, p, is 20%, or 0.20. And the math here is beautifully simple. By just multiplying n by p, we find the expected value. 40 times 0.2 equals 8. So the medical team can mathematically expect 8 survivors. We can even calculate the variance to see how much that expectation might fluctuate. It's incredibly powerful stuff.
All right, part 3, Poisson. Timing is everything. We are stepping up the ladder once again.
We're shifting our dimension here. We're moving away from counting fixed events to tracking events over time or space. The crucial divide here is that we are completely abandoning the idea of a fixed number of guesses or a set group of patients. With the Poisson model, there is no n. Instead, we are measuring how many times an event pops up during a set window of time, or within a specific physical space. So you aren't asking how many heads will I get in 10 coin flips anymore. You're asking how many customers are going to walk through my front door in the next hour. Now, just like the binomial model, Poisson has its own strict rulebook you have to follow. First, the occurrences absolutely must be independent of one another. Second, they have to happen at a constant average rate. We usually represent this with the Greek letter lambda. And third, they feature what's called singularity. That sounds pretty sci-fi, but it just means events cannot occur simultaneously at the exact same microscopic fraction of a second.
When you follow those rules, Poisson gives business owners and scientists a ridiculously powerful predictive tool. Let's say a company switchboard gets an average of 2.5 phone calls per minute. That 2.5 is our lambda. We plug that straight into the Poisson formula to figure out the exact probability of getting, say, exactly 4 calls in the next minute, or maybe dead silence with 0 calls. And it's the exact same math whether you're measuring 5 emitted particles per second from a lump of radioactive material or a ticket counter seeing 3 arriving customers per minute. If you know the average rate, Poisson lets you predict the chaotic, real-world fluctuations around that average.
Moving on to part 4, the continuous normal distribution. It is time to start measuring reality.
We are now breaking away from counting whole numbers entirely. Notice the major visual shift here. This is the famous, smoothly sloping bell curve. Those blocky steps from our previous discrete distributions, completely gone. We are no longer counting distinct things like 1 phone call or 2 phone calls. We are now measuring things that can fall anywhere on an infinitely sliding scale. This beauty right here is the normal probability distribution, though you might also hear it called a Gaussian distribution. Now, it might look like just a simple, gentle hill, but the math under the hood is incredibly strict. A true normal distribution has a single peak right at the dead center. It's perfectly symmetric, meaning if you folded it in half, the left side is a flawless mirror image of the right. Because of that perfect symmetry, the mean, the median, and the mode are all exactly the same value. The tails of this curve are asymptotic, meaning they stretch out infinitely to the left and right, getting closer and closer to that bottom line, but theoretically never ever touching it. And crucially, this is a big one, the total area under that entire curve equals exactly 1, which represents 100% of all possible probabilities. So why does this matter? Because reality is rarely exact, but it is, quite often, normally distributed. Let's say a factory makes cereal boxes that are supposed to weigh exactly 32 ounces. In reality, some might weigh 31.9 ounces, maybe some hit 32.1. Manufacturers rely heavily on the normal distribution to predict exactly how many boxes are going to roll off the line slightly underweight. Or think about manufacturing steel rods to a 20-centimeter spec. If the lengths follow a normal distribution, engineers can calculate the precise percentage of rods that will have to be rejected. We even use this in agriculture to predict how many plots of land will fall below a 660-kilogram crop yield. It literally is the mathematical footprint of nature and industry.
And finally, part 5, standardizing the normal curve. Let's hit that last rung on our complexity ladder.
So here is the giant headache with the real world. Every single scenario has a totally different average and a totally different spread. You've got cereal in ounces, steel in centimeters, crops in kilograms. Doing complex calculus for every unique, individual bell curve would be an absolute nightmare. To solve this, statisticians use this incredibly elegant trick called the z-score transformation. And honestly, it's pretty simple. You take your individual value, subtract the mean of your dataset, and divide that by the standard deviation. That little bit of math standardizes the chaos. It converts any unique bell curve into one neat, highly comparable standard curve.
What this does is turn the standard normal distribution into a sort of universal mathematical translator. It strips away all those messy real-world units. It just completely deletes the ounces, the centimeters, the kilograms. By doing that z-score transformation, we are always left with a standardized mean of exactly 0 right in the center and a standard deviation of exactly 1.
And by standardizing, we unlock a massive shortcut. We don't have to do agonizing advanced calculus anymore. We can just take our z-score and use universal standard normal probability tables to rapidly predict exactly where any single event falls on that curve. Whether you want to know the probability of a z-score being less than 1.33 or falling exactly between 0.55 and 1.22, you literally just look it up on a pre-calculated grid. It makes dealing with the infinite complexities of continuous data incredibly fast and incredibly precise.
So, look how far we've come. We climbed from a single, simple Bernoulli coin flip all the way to standardizing continuous Gaussian curves. We can successfully model radioactive decay, predict cancer survival rates, and even map out Supoon's terrible guessing habits on a test. But I want to leave you with this. Think about your own daily life, your commute time, your daily coffee consumption, or the flood of emails you get every single morning.
Which of those are distinct events you can easily count, and which are continuous measurements? Understanding these tools fundamentally changes how you view the probability of your own world. The math isn't just locked away in some textbook, it's happening all around you, every single second. See you next time.